Okay, so today we will start part 5 of our chapter. Okay, so this is going to be a more, as I said in the last video, in the tutorial video, about the solution set of a linear system. Okay. Today's lecture is going to be how to describe that solution set in a more elegant way. And the solution set of a linear system is described as follows. General solution, okay, is written as particular plus homogeneous. Homogeneous. So that means a solution set of a linear system has two parts. It has a particular part and a homogeneous part. We will see shortly what is or how can we detect the particular part and or how do we define the particular part and how do we define the homogeneous part. Okay, so this part 5 of the chapter is going to be divided into two sections. Section A, I'm going to do the definitions. We will see some definitions, and in part B, in another video, it's going to be a short one. We will see a very small, very but important concept. Okay, but for now, let's define some important concepts first. Okay, if you recall, a linear system, the solution set of a linear system. Okay, a linear system has two types of solution sets. Okay, the solution set can be infinitely many. Okay, so let me write it here. We have we can have infinitely many solutions. We can have a unique solution, and finally the third type is we can have no solution at all. Okay, so let me write the infinitely many solutions. Okay, how do we describe it? As particular plus homogeneous. If we recall from our last video in the tutorial, the solution set for the given linear system was 5 minus 5. Okay, so 5 minus 5, 2, 0, 0. Okay, so plus, okay, let me write it like this. The solution set, we have our x, we have x, y, z, w, u equals to 5 minus 5, 2, 0, 0, plus we have minus 7 over 2, 5 minus half, 1, 0, w plus minus half, 0, minus half, 0, 1, u, such that w and u can take any value in R. That means w and u are free. Okay, that was the solution set. So here, this is our general equals to, this is the particular, is the constant, the vector of constant, the constant vector, if I can say so. So this is the particular, and here we have the homogeneous. So plus, this is the homogeneous part. So here is the linear combination of some vectors. That's the homogeneous part. So that's how we describe the solution set of a linear system, to find a particular solution and its homogeneous parts. So it's very easy to describe for infinitely many solutions. Let's now have a look for um, unique solution. So yeah, unique solution. A unique solution is just written as follows. So we have, let's say, x, y, z, okay, which is equal to 1, 0, 1. That's how we describe a unique solution. It's just made of the particular parts. Okay, so, and let me give myself some space here. Okay, but because I need to write something here. So, uh, so that's the unique solution. Okay, I want to make things better to understand. But here, inside here, okay, inside here, we can assume that there is a combination of 0 vectors. Okay, so let's say w plus 0, the 0 vector is going to be 0, so that's why we have nothing here, but let's call it combination of 0 vectors, or no vectors, of no vectors. So that's how we write the solution set of a unique solution. We have a general equals, here is the particular, it has only particular parts, and here this is the homogeneous part, okay, plus the homogeneous. So you can see it makes sense. We can write, we can describe the 3 types of solution set in this way, as a general equals to particular plus homogeneous. Okay, now when it comes to the third one, is the empty set. But before we do the empty set, let me give you a quick note. Okay, note that by convention, the sum of empty sets of vectors is the 0 vector. So the sum of 0 vectors, an empty set vectors is the 0 vectors by convention. I know it is a bit weird, but hey, computations must make sense, so we have to go by some conventions. So by conventions, otherwise our calculations won't make sense. Okay, by convention, the sum of an empty set of vectors, okay, so in an empty set there is no vectors, so the combination of no vectors is the 0 vectors. Okay, so the sum of the no vectors is the 0 vectors. The set of vectors is the 0 vector. Okay, just by convention. Now let's go to describe the empty set. When we have no solution, that means we have an empty set. Okay, so how do we write no solution? If you recall, how do you describe, or how do you write down no solution? It's just the empty set. So we have the empty set like that. Okay, So the general, okay, let me make it a little bit clearer. So let's say we have x, y, z, and w equals to the empty set. Okay, so equals to the empty set, so that it's we follow the same logic, okay, as the previous ones. So here, how am I going to describe here? So here I have the empty set, but here as well we are going to have no sum of that vector because it's empty, so there is no sum at all. Okay, so there are, because if something is empty, that means there are no sum of the vectors. Okay, so there are no sum. Excuse me, no sums there. So of the vectors or of any vectors. So here we have the general equals to the empty here. This is here, and so that means we have no particular sum, no particular, okay, and we have the linear combination of no particular. So it makes sense, right? I know it sounds weird, but it is. Do you see the logic? Because the particular is there is no particular. Therefore, we have a plus no combination of no particular. So it should make sense. So here, that means here we have that means here we have the homogeneous. Nothing. Therefore, we have no combination of nothing. So it makes sense. Okay. So let me go to the next screen with let's continue the definition. Yeah, here I should write down um, introduction. Part A, section A, but we have many things to see here, so this is the introduction. Okay. Theorem. Let's see this theorem. Okay. So it says any linear system solution set has the following form. Linear systems, okay, solution set has the following form. So solution set is written as the particular plus linear combination of some vectors plus C1, B1 plus C2, beta 2, sorry, it's not B, it's beta, plus CK, beta K, as you have just seen in the introduction, right? Such that C1, C2, CK are free, okay? They are the free variables. So where P is any particular solution and where the number of vectors b1, beta1, beta1 to the okay equals the number of free variables, of course, equals, as we have seen so far, the number of free variables that the system has after a Gaussian reduction. That the system has after a Gaussian reduction. Okay, so I think this theorem is easier to follow based on the introduction we have just seen. Okay, so let's continue with what do we mean by a homogeneous part. Number 3, let's continue with the definition. Okay. Okay. A linear equation is homogeneous if it is written as follows. So a linear, okay, we are going to linear equation, a homogeneous equation we are going to define here. A linear equation is homogeneous. Is homogeneous if it is if it has a constant of 0 so that it can be written as so it can be written as okay, here is how we write a1 x1 plus a2 x2 plus an xn equals to 0. Okay, so the constant of the equation is 0. So if the constant is not 0, it's no longer a homogeneous. We just call it non-homogeneous equation. Okay, so good. Let's continue part 5 with a very interesting lemma here. Part 4, sorry, lemma. The lemma says for any linear system that is homogeneous, there are vector b and k such that the solution set is written as we will see shortly. And you will see also the beautiful thing about a homogeneous equation. You will see shortly and you will appreciate. Okay. For any homogeneous linear system, there exist vectors beta1, beta2, beta k such that the solution set of the system is written as C1 beta 1, okay, as we have seen here, the homogeneous part, beta 1 plus C2 beta 2 plus CK beta K, such that C1, C2, CK are free, okay, where K is the number of free variables in an echelon form version of the system. Okay, so let me give you a small example here. Okay, let's say we are given the following linear system. So we have x plus 2y plus z equals to 2x minus y plus z equals to 3 minus 4x minus 3y minus 3z equals to minus 7. This is our original equation, okay? So this is original equation or system. Let's call it the original system. Now let's have the homogeneous system. Okay, so the associated homogeneous system is going to have what? Is going to have 0 constants. Okay, and so we'll have x plus 2y plus z equals to 0. I think it's good to make that 0, to highlight that 0. Okay, so yeah, it goes like this. First 2x minus y plus z equals to 0 and minus 4x minus 3y minus 3z equals to, so that's 0, 0, 0. Okay, so that's the associated homogeneous equation. And after this lemma, I want to give you some observations, but so that you can see clearly the observation or some observations, so that you can see clearly those observations. Let me solve these two types of systems. Okay, then the original system and then the homogeneous system. So let us solve it, and you will see something. And you will see the beautiful thing about the homogeneous systems. So here we are still in our example. Okay, let me say here solving. I am still doing the example. So let us solve the original system. Solving the original original system. Okay, to be able to solve the original system, let's rewrite it and perform Gauss's method. Okay, I want to use the augmented matrix because I just want to go. I want to just show you um, some observations. So let's just perform the Gauss's method on the system as it is without using augmented matrix. 2x minus y plus z equals to 3, and minus 4x minus 3y minus 3z equals to minus 7. I think my 3's and z's kind of look the same. Okay, so let us solve this system of equations. First of all, let's perform Gauss's method. So minus 2 rho 1 plus rho 2. Now we should be champions in Gauss's method, so I won't explain too much how it works. I just apply it. So we have x plus 2y plus z equals to 2. So minus 2 times rho 1 plus rho 2. I have a 0 here. So minus 4. So I have minus 5y there. Minus 2 plus 1 is minus z equals to minus 4 plus 1 is minus 1. Okay, and for the third system, for the third row, I have 4 times rho 1 plus rho 3. That will give us, okay, that's 0, 4, that's 8, minus 3 is going to be 5y, 4, that's going to be z, okay, and this is going to be 8 minus 7 is going to be 1. And let me continue with the last step here. So I'm going to use the minus 5y here to eliminate the 5 in the third row. Okay, so I'm going to do rho 2 plus rho 3. This will give me x plus 2y plus z equals to 2, and minus 5y minus z equals to minus 1, and here we are going to add rho 2 to rho 3, so that's 0, that's 0, so we have 0 equals to 0. Okay, so here these are the, okay, I won't tell you yet, but let's do the same thing for the homogeneous system. Okay, solving the homogeneous, the associated, not any homogeneous system, but the homogeneous system associated with this original system. So let's solving the associated homogeneous system. Okay, so the associated homogeneous system is x x plus 2y plus z equals to 0, 2x minus y plus z equals to 3, and minus 4x minus 3y minus 3z equals to minus 7. Okay, so let's solve it. We are going to do minus 2 rho 1 plus rho 2. Okay, so we have x plus 2y plus z equals to 0. Sorry, this is the homogeneous system. Let's be focused here. So the constants are going to be 0. Okay, so minus rho 2 minus 2 rho 1 plus rho 2. This is going to be 0 minus 2. So is going to be minus 5y, and here is going to be minus z equals to 0. Okay, and for the third row, we have 4 times row 1 plus row 3. We're able to cancel the x term, so we have, okay, that's cancelled. 4, 8, so we have 5y plus z equals to 0, and the last part is going to be, we are going to cancel that 5y, so we have row 2 plus row 3 will give us x plus 2y plus z equals to 0, minus 5y minus z equals to 0, and 0 equals to 0. And I don't know if you have seen something. Can you see that for the two systems, the reduction systems steps are the same? No matter what the constant was, that means no matter if we are dealing with the original system or the homogeneous system, we are performing the same steps of reduction. So here, this one is the same as this one. Okay, let me change color so that you can see. Okay, and then the second reduction system is the same as here. And then the third reduction system here, the third one is the same for both the original and the homogeneous system. So the reduction systems are the same. Okay, that's that's very important for our next observation. So note that the reduction steps, okay, the reduction steps for the two systems, that means, I mean, the original and the associated homogeneous one. Okay, so I mean the original, original, or is also known as a non-homogeneous. Homogeneous, and the associated homogeneous. Okay, so the reduction steps for the two systems are the same. Okay, so let's continue with the observations. Okay, so let's continue with the observations, as I say. Observation, so number 6. Okay, 6, we need to do some important observations. Maybe let me go to next slide so that I can have all the observations on the same slide. Okay, so number 6, observations. What have we observed so far? Okay, number 1, we have observed that one can study the reduction of a linear system by instead studying its associated homogeneous system. Based on the example we have just seen, The reduction steps are the same for both the original non-homogeneous system and the homogeneous system. So instead of studying the original system, we can study the homogeneous system because of what? Because the homogeneous system will always have a solution. It will have either a unique solution or infinitely many solutions. You see, the reason why homogeneous systems are very beautiful because they always have a solution. Okay, let me write it down. Okay, so first observation is one can study the reduction of a linear system by instead studying its associated homogeneous homogeneous system. Let me squeeze it there. Okay, why? Because the homogeneous system always has a solution. Okay, because the homogeneous system always, let me write it in bold, always, okay, always has a solution. Okay, the solution can be either infinitely many solutions or a unique solution, but that unique solution is going to be the trivial one. That means the zero vector. Unique solution, which is the trivial, we call it the trivial solution. That means the zero vector. Zero vector. Okay. Another observation, number 3. So, based on the first two observation, studying the homogeneous system is consistent. Okay. Because non-homogeneous systems can have some inconsistencies since they can have no solution. So there is some inconsistency and some difficulties related to the fact that there is a possibility that they have no solutions. But when it comes to homogeneous system, it always has a solution. So, it's easier and better to study. Making the homogeneous system consistent. Okay, to study. Because the non-homogeneous system can have some inconsistency, can be inconsistent. Can be inconsistent, okay. So, based on the above three observations, therefore, uh, basically that means that the homogeneous system has a great advantage over the non-homogeneous system. And you will see from now on, and a great part of linear algebra is based on homogeneous system. Okay, so from now on, we will be focusing on homogeneous systems. Okay, so therefore, okay, studying the associated homogeneous system has a great advantage over studying its non-homogeneous, that means the original system. Okay, so let's have a look at this lemma. Okay. Lemma, it says the following. Okay, it says for any linear system and for any particular solution P, the solution set equals to the following. Okay, let's go. For a linear system and for any particular solution P. From now on, when we say particular solution, you know what you mean. Okay, the constant vector, the vector that has no that is not being multiplied by any scalar. Okay, that's the constant vector. So for it and for any particular solution P, the solution set equals, okay, we write the solution sets like this: P plus H, the homogeneous part, such that H satisfies this, satisfies the associated homogeneous system. Okay, I won't prove any theorem, lemma, or corollary in this lecture or in this module, but if needed, you can just send me an email and I can do a short video to prove all these theorems, lemmas, and corollaries we will see in this module. They have proofs and I can prove them to you, but I don't want the module to be too long, so I will save you from the proofs. But they are beautiful. They are beautiful though, if you need them. Okay, corollary. Okay, the corollary says the following: solution set of linear systems are either empty, we have already seen them, but are either empty or they have a, a unique element, have an element, okay, or they have infinitely many elements, or have infinitely many elements. Okay, so that's good. And let's finish this with the following summary, this section. Okay, so let's finish this section with the following summary, okay, of the factors that affect the size of a general solution. Okay, so how would you know if you have a unique solution or infinitely many solutions? Okay, so let me write here factors affecting. It's just a summary of sometimes it's good to have a visual picture of everything we have just said so far. Factors affecting the size of a general solution. Yeah, let's see, I hope I will have enough space here. So when we are given an equation, okay, we will ask ourselves, does it have a particular solution? Particular solution. If because it has at least if a solution has if a system has a solution, it must have either a particular, it must have at least a particular solution, but it has, if it has so sometimes that particular solution can be the zero vector when we are dealing with the homogeneous part. Okay, when you have we have seen here the solution set can be written as P plus the H, which is the homogeneous part. But sometimes we may not have P, or the P can be indirect. That means it can be zero, the zero vector. So we don't write zero plus the combination of whatever vector. We just write the homogeneous part sometimes. Okay, so when a system has a solution, it must have at least the particular solution, or which is maybe sometimes the trivial one. But when it has no solution, no particular solution at all, that means the system has no solution at all. Okay, so we have two options here. Do I have enough space here? No, let me write it. Let me do this so that I can have enough space. So we have the number of solution of so let me write here, we have the number of solution of the homogeneous system, of solution of the homogeneous system. We have seen so far that the homogeneous system can have two solutions, okay, either a unique solution or infinitely many solutions. So we have here either a unique solution, unique, or infinitely many. So now let's split this into two. Oh, okay. Let's split this into two. Okay, so let's ask ourselves, does the system have a particular solution? Okay, so let's ask ourselves, particular solution exists? Okay, we have two options here, either yes or no. If we have no particular solutions at all, okay, we have two options here. If we have no particular solutions at all, that means we have, no solutions for the system at all. No solutions, no solutions. But if a particular solution exists, okay, sorry, I should say here, 1, just to make some small difference here. So if a particular solution exists, then the system has either a unique solution, the whole system, okay, or infinitely many solutions. Infinitely many solutions. So we can have informations about the original system by studying the homogeneous system. Okay, so if the system has no particular solution, that means the system has no solutions at all. But if the homogeneous system has a one, that means the original system has a unique solution. If the homogeneous system has many solutions, that means the original solution has infinitely many solutions. Is that okay? So I think I'm going to stop here, okay, and I will see you in the next video. Okay, thank you.